Hossam, I haven't had a chance to meet you personally in the past. I heard a lot about you and I looked a lot on the web, and here is the list of unbelievable achievements and activities that you are doing. So they don't need me to add anything to it. And of course, here you add the IVS prize that you share with Ernesto for this year. By the way, I want to say one thing. It has been extremely competitive and extremely difficult to select this prize. There were many very, 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 very qualified candidates, and you guys stood above, and it reminded me, you know, I used to follow Formula One in my youth, and sometimes you have the arrival and you have the two cars that arrive, mamash, one close to the other, 1,000,000th, 1,000th of a second, one from the other, and basically the two arrived at the same place. We had one prize only, so what do we do? So we had a whole discussion with the evaluators. By the way, I had no input on it. I was just an administrator counting the scores, and I was just there. Hossam and Ernesto, what do we do with these two? They are together. So we decided they are together, they're together. And so here we have this. I want to say just one word. Hossam, I like to learn, and I saw also that you pride yourself on teaching, and I saw that you have a course on Coursera, which is a website that has a lot of classes. And I saw very, very high rating. It's on my to-do list, a very long to-do list of things to do. I want to check your course out. So I think, unfortunately, I was too fast. It's 9:25. First of all, before starting, are there any questions on how this works, or from you or from the audience? So I don't know if we start right now or we wait another 5 minutes, because we said we would start at 9:30. Sydney, what do you think?
Let me just say a word about the fantastic job of Danielle. I don't know if you sleep, but I don't feel that you sleep a lot. At least you will have a bit of sleeping for the next days during Hanukkah. So thanks really from all the people that were involved into the preparation of the meeting. I'm sure it will be fantastic. And second, I mean, I will just have to thank all the speakers from abroad that did it on a Sunday. It was not easy. So amazing.
And especially the ones from America that have either to stay up night late or wake up very early for this conference. Yeah. Okay, so maybe I would say maybe we can start. Hossam, what do you think?
Okay, should be
Ready?
fine. Let's just start preparing the sharing.
Go ahead.
Okay, let me see. Do you see my presentation?
Yes.
Okay.
Excellent.
That sounds great. First of all, I would like to thank you for the introduction, and of course, and most important, also to thank the organizing committee, as well as the awards committee of the IVS for selecting me together with Ernesto for this IVS award. So this brings to me actually two privileges. The first, it's because from my almost home institute, starting from the time when I spent a postdoctoral fellowship in the group of David Cahen back at the Weizmann Institute, then was my first time to get to know with the IVS. And secondly, to share a prize with Ernesto Joselevich, a great scientist, which I have always admired. It's a true honor for me as well. So this is truly special award for me this year. And I thank you again for the trust that you have put in me and in Ernesto and in both of us. Of course, I do recognize that the qualities of the other candidates are absolutely high, and appreciations will come in the following. Today, I will speak about what we have done in the last few years in one part of the projects we do in our group. And I will talk about the so-called advanced electronic sensing platforms with skin-like capabilities, what we call electronic skin. I would like to start with a little bit introduction. What is skin? Skin is one of the largest organs in the human body, both in terms of surface area and weight. It has three main functions: protection, regulation, and sensation. In its role as a barrier, the skin provides protection from mechanical impacts and pressure, variations in temperature, microorganisms, radiations, and chemicals. And on the other hand, the skin regulates several aspects of physiology, including body temperature throughout sweat and hair, and changes in the peripheral circulation and fluid balance throughout sweat. For our discussion today and my presentation, of a special interest would be that the skin has simultaneously separate receptors of heat, cold, touch, and pain, something that we want to imitate for wide variety of applications. Reproducing the capabilities of the human skin to respond to environmental factors while maintaining long-term durability and survival is one of the most important for wide variety of fields, including healthcare diagnostics and monitoring throughout wearable devices, electronics, robotics, and many more. Those devices which mimic such properties of a human skin, along with additional features, we commonly refer as electronic skin, or abbreviated as e-skin, something that you will hear several times throughout my presentation today. In our previous work, we have employed autonomic self-healing components to create the first entirely self-healing multifunctional field effect transistor. The devices were back then based on carbon nanotubes, single-wall carbon nanotubes, and self-healing polymer. In this case, it was polyurea urethane, PEU. And this PEU was adopted as a substrate and as a dielectric layer, using reversible hydrogen and disulfide bonds to achieve autonomous recovery in the absence of any external stimuli. On the other part of the device, semiconductive carbon nanotubes, again single-wall carbon nanotubes, were coated into the surface of the PEU to obtain the self-healing semiconductive channels of the FET. Namely, all the parts of the FET are based either on carbon nanotubes with PPU or PEU alone. The self-healing of the polymer, which have examined back then, allowed the so-called induced recovery of the ultra-thin carbon nanotube films, and all the conductive components which you see on the right side of the slide of the FET, which include source drain electrodes, gate, and semiconductive channel, showed good self-healing efficiency, which enabled the recovery of the whole transistor-like behavior even after severe cuts, even if cut it completely. So far, this device we have applied as electronic tattoo, which you can see here on the bottom part of the slide, that can be attached to the skin with the high conformity. And this allowed very efficient monitoring of physiological parameters and diagnosis of disease such as tuberculosis, something that we have done with the Bill Gates Foundation and with the involvement of Bill Gates by himself. So because this is not a clinical or medical conference, so I will escape this part, but I can tell you that we have examined these tattoos on more than 1,000 patients in South Africa, in India, and in Latvia, and the results that has been received in real clinics was 92 to 97% accuracy with the detection of TB. Something that is quite important in light of what we are suffering or what we are feeling these days because of the COVID-19. An evidence of the self-healing ability of each part of the FET, we have cut the device, as you can see on the left side of the slide, using a sharp blade, and then we have monitored the structural recovery and the performance with time. The upper left figure shows optical images of the healing process of the structural damage after a blade cut made perpendicular to the conduction pathway. And as you can see, the conductive film can recover from drastic cut quickly and maintain good conductivity. In this case, the cut was 5 micrometers in width and 2 micrometers in depth. In the bottom left figures, you can see very sharp increase in the conductivity at the beginning of the recovery, which decreases with time to reach the plateau. And this is probably due to the recovery of the elastic polymer near the damaged area, as well as the surface rearrangement and diffusion of the polymer chains of the PEU. On the right side, upright side, you can see the effect of the mechanical damages on each part of the FET structure. The behavior of the FET was almost totally recovered after 1 hour. Actually, it's 95%, and we have to wait another 23 hours in order to get to 99% of the recovery. And in this case, the gate electrode could heal several cuts with negligible change in the performance. And we have, of course, several demonstrations and videos, so I will escape those today because of the low quality of the videos and its presentation on the Zoom. Right now, despite the recent advances even though which I have mentioned in my previous slides, the implementation of the self-healing electronic skin and the real-world conditions, which is characterized by a lot of contaminations and humidity and variations and confounding factors, are still hindered by several challenges which you can see on the screen. The first challenge is the need for a new self-healing polymer with improved electronic properties that could enable integration with digital circuits. The second challenge is the need for balance between the material's stiffness and mobility. And the third challenge is the need for non-demand self-healing system that selectively trigger the self-healing process in designated locations in the integrated electronic system. And the fourth challenge is the need for a device that works under a wide spectrum of harsh environmental conditions, such as underwater, even those contaminated water, or under very high humidity levels. And the fifth challenge, which you can see, is the need for multifunctionality that enables simultaneous sensing and decoupling between the multiple physical and chemical properties. In the next slides, I will show an advanced approach for electronic skin that should overcome most of these challenges, something that we have worked on in the last 4 years. And we could achieve, in general, this target by mimicking several aspects of the human skin properties, starting from the use of new hydrophobic polymers, along with the integration in a multi-layer device. The electronic skin top layer contains multiple sensors, which I will explain a little bit more in the next slides. And those are designated for detecting environmental signals, whereas the other layers introduce a controlled feedback system that selectively accelerates the self-healing process at a designated locations. As a first step to reach our ultimate goal and to overcome all of these challenges, we introduced a new self-healing thermoplastic elastomer for use under harsh and complex humidity and water conditions. By the way, self-healing under water conditions is quite rare, or at least was quite rare a few years ago. And for this purpose, we have synthesized a new polymer from hydroxyl terminated polyputidine, which we abbreviate HTPB, that is extended by isofron diisocyanate and 4-aminophenyl disulfide by 2 main reactions, which you can see here in the middle of the screen or the slide. And in this structure, the polyputidine parts of the formed elastomer contributed low temperature flexibility and superior water resistant. On the other hand, the 4-amino phenyl disulfide component contributed dynamic disulfide and hydrogen bonds when the urea or the urethane linkages were formed. The existence of the two integrated mechanisms for self-healing that are based on covalent and non-covalent bonds, namely the disulfide and the hydrogen bonds, respectively, and the high softness of the polymer make it very efficient self-healing material, which you can see in the bottom side of the screen. I'm trying to sign. I hope you see this cursor. In order to understand a little bit what is going on with these polymers, we have run simulations of molecular dynamics, and we have shown throughout these simulations a separation between the soft and the hard regions of the self-healing polymer, something that we have confirmed by TEM analysis. The simulations briefly shows that the water molecules can only interact with the hard regions, and they barely diffuse into the soft regions in the new self-healing polymer. The hard regions don't form a continuous pathway into the polymeric bulk, and therefore, overall, this could explain why these polymers are not sensitive to water, something that reaches our ultimate goal, which we have designated beforehand. In this slide, you can see in the top left images the ability of the polymer to recover its elastic properties after complete cut. And the right images, on the other hand, shows the full regeneration of scratches within 24 hours under ambient conditions. Of course, in this slide, we can see similar behavior towards the scratches and complete cuts in underwater conditions, even though these water conditions, our water, are brought from the Mediterranean Sea with a lot of contaminations. And since our one of our goals was to introduce superior resistance to humidity and water conditions, we tested the self-healing ability of the new self-healing polymer under different aqueous environments, including tap water, acidic seawater with pH of 3, more or less, and basic solution with pH around 11. And here the results on the screen shows that the self-healing efficiency under all aqueous conditions was comparable to the healing observed in air. This water insensitive self-healing capability originates from highly hydrophobic water resistant the repeating unit of the polybutadiene, which we have introduced into the polymer. Based on the advances with the design of the new polymer, which I've explained in the previous slides, we have designed a multi-layered device that integrates a sensing layer, a neuron-like nanostructured network for self-monitoring, a damage detection, and an array of electrical heaters for selective self-repair. The top layer was the sensing layer. It included 3 different types of sensors: pH, temperature, and pressure sensors. For temperature sensing, we used a resistive pattern of silver nanowires that are embedded within the new self-healing polymer. And in this case, we found that the self-healing structure and the self-healing temperature sensor to be very sensitive both before and after the recovery from structural damage. Even complete cut, we could get to the original values of the temperature sensing. For the pressure sensing, we used a resistive composite made of self-healing polymer and carbon black. And the application of the pressure led to an increased distance between the conductive fillers and therefore to increase in the resistance. And examinations that we have run in the lab, and for the time limitations which I have in my presentation, I cannot show all the results. We have shown that the composite is very sensitive to pressure as low as 200 Pascal and has shown a high recovery before and after mechanical damages.
3 minutes.
Okay. For the pH, we used the semiconductor carbon nanotubes as the sensing layer, and the device showed higher on currents under basic conditions, and therefore you can see that the pH sensor was quite successful also in this case. I will go to the more important slide before we finish. The second and the third layer included resistive networks that can be used to monitor the structural integrity of the electronic skin. And more specifically, we designed a neuron-like nanostructured network of conductive carbon black that is embedded inside the new self-healing polymer for mapping and determining local damage. With this design, we could achieve accelerated recovery of the detectable damaged parts by integration of an array of self-healing electrical heaters that apply local heat to the damaged areas and therefore lead to very efficient acceleration of repair. The heaters were composed of silver nanowires network that are embedded inside the polymer, and this heating-induced repair process lead to the healing of superficial crack in 30 seconds only, instead of 24 hours as in the previous polymer, or in 5 minutes in the case of really heavy cut or damage, which otherwise in the previous polymers we couldn't get even after 48 hours at 70 centigrades. In my last slide, I want to show you a demonstration of the functionality of the integrated high autonomic electronic skin. And here we can see that the damage detecting network that we have designed to be close to the functional sensing layer could allow detection of the damage in quite useful way. In the case of small scale damage, in this case below 100 micrometer in depth, the intrinsic self-healing capability operated only at recovery. However, once the damage is large enough, namely above 100 micrometers in depth, both the intrinsic self-healing and the self-repair mechanism could be operated until we got the complete recovery. As you can see on the right side of the slide, cutting the temperature and the pH sensors by a blade down till the DDN layer, namely the damage detecting network layer, led to the activation of the heater, which in turn increased the local temperature and led to complete heating of the device. And finally, you can see that this mechanism could work also for the pressure sensor and the other devices that we have put and integrated in this electronic skin. With this, I would like to summarize briefly that with tailor-made and personalizing the polymers and the hybrid structures, we can receive electronic skin that could be multifunctional in terms of its activity as a sensor, which can simultaneously sense a lot of stimuli, both physical ones and chemical ones. The self-healing could be reached within 30 seconds and sometimes 5 minutes, which is quite applicable and good for real-world applications, mainly in robotics. At the end, I would like to thank my group who worked in this field, and mainly Muhammad Khatib, who has led part or a major part of this work, and today he's in his way to Stanford for his postdoc in the group of Jinan Bao. So with this, I would like to thank you again for your attention. Thank you.
Thank you. Thank you, Hossam. So we had even the applause today. So now we open up for questions. Anybody in the audience, you can ask with the Q&A or with the chat to speak. We can let you ask questions, or any of the panelists here, and we have quite a few people on it. Any questions? Yes. Ray Boxman?
Yeah, can you explain to us what the self-healing mechanism is In other words, what happened? How did it heal itself?
Okay, as I have, just a minute, I will remove the share. Um, as I have mentioned earlier, we have the sulfide and we have the disulfide. We have the hydrogen bonds. Once we cut, in the middle of a self-healing polymer, we will have hydrogen bonds and we have disulfide bonds. And as you can see, the hydrogen bonds are, in some case, are irreversible, and therefore, once we cut, we will get a high surface energy that that has in autonomous way has to decrease. And the only way is that the hydrogen bonds with the disulfide bonds on the other sides will reconnect again until they reach the complete self-healing. This is and therefore this happens gradually, that you can close up the gap in this way by reconnecting the chemical bonds, which I have mentioned, either the disulfide or the hydrogen, in systematic way. Of course, the polymer, once you cut it, produce these two parts of the hydrogen and the disulfide bond.
Hossam, I have a question here from Tomer Zimrin. He asks, can you refer to self-healing of the non-polymeric parts?
I try to understand. Can
the
you refer?
self-healing of the non-polymeric part? I also had that question because you have a lot of circuitry there, nanotubes and other things.
You're right.
How do they recover?
We have a random network. We have random network of carbon nanotubes, which it's like interdigitated carbon nanotubes. So once you cut it in the middle, what happens is the fact that the polymer itself, or the underlying polymer, will start to recover, and based on that, it will induce the recovery of the carbon nanotubes to bring them back together. And of course, because this is not a few single carbon nanotubes, but rather a network or a two-dimensional layer, so any mismatch with the carbon nanotubes still don't affect the bringing the reconnection of the carbon nanotubes and their electrical properties together back.
Okay, just one last question I see from Sydney. Sydney Cohen is asking, what is the reason for the drop in strain to failure between pristine and air environment and further in liquid environments?
Sorry, again?
So he asks, what is the reason for the drop in strain to failure between pristine and air environment? And he also asks about in liquid environments.
It's about the sensitivity to water molecules. The water molecules, in this case, once we have, by the way, I have presented two polymers, so I don't know whether one you refer to, but anyways, in the case of the water molecules, once they adsorb on the surface, they eliminate the reconnection of the bonds in quite efficient way, and this could lead also to these changes in the strain.
Well, Sam, thank you very much. It was a very amazing presentation. I have some questions also on my own, but we're really running out of time, and it's night for Ernesto. So thank you very much. Very well deserved and very beautiful presentation. Thank you.
Thank you very much.
So now I want to introduce Ernesto. Ernesto Joselevich. He is a professor in Weizmann in the Department of Material Science. Also, he has too many prizes for me to spend time to list, as it was for Hossam. I want just to say one thing that is just a personal observation of Ernesto, is I've heard him speaking many times, and every time I enjoy it really very much, and I told it to him, and it's not just flattery, it's true. There's one thing I like a lot. When I learned in my PhD, my advisor was pinning me on understanding the mechanisms of why something happens. And he always said, you know, something that is gonna last, and besides it is something that explains what is happening. And I really enjoy his presentations. First of all, they're kind of close to my areas of research. And also he spends much time to make you understand what are the physical, chemical mechanisms for what happens, and that's the hard part of every type of research. So Ernesto, without further ado, I want to leave you the stage for your presentation, and as my advisor used to say, go ahead, razzle, dazzle, and impress.
Thank you very much, Daniel, for this very warm introduction. And I want to thank the organizers for putting together this amazing program and giving me the opportunity to give a plenary talk. Hold on, I don't know why. This is another minimize, optimize full screen. It was okay before. Just a second. I don't know why it's taking some time to share, but it's coming up. So, and I want to thank the. Can you hear me?
Yes, you can hear very well.
I want to thank the committee for giving me this prize and for the Solomonic decision, because I really admire Hossam as one of the giants in the country in the field of nanotechnology. So for me, sharing this prize with him is a great honor.
I suggest that you share without optimizing the thing, and when you come to your video, you disconnect the sharing and you share with the just for the video. Well,
okay.
How about that?
Okay, let's try again. No, but hold on. I want to see what's going on, because there seems to be a problem with the file itself that I don't see. Just 1 second. I want to close it and open again.
Okay.
Hold on. I'm sorry for this. Okay, I think it should be fine now. How is the no? I want to try to use this feature again. How do I do this?
There was the
it is already there. Okay, can you see my
yes,
my screen?
Yes, excellent.
Okay, so today, you know, it's not a lot of time, so I didn't want to show too much, but to focus on one story that is an ongoing story. Actually, the most exciting part of what I will show is not published, so it's for your eyes only. And it's about the kinetics and mechanism of guided nanowire growth. I will start with a very brief background about the topic,
Ernesto,
if I have to cut something, it will have to be something in the middle, because at the end I have some nice movies that I definitely must show you.
Ernesto, just remove on top where you have probably the fixtures of the panel, close it, because it comes as a black stripe on top. Yeah, that thing on top.
I don't see the pictures from the panel.
I don't know, you have a line on top, a strip on top that is covering the title.
Maybe I'm sharing the screen instead of the, hold on. How do I do this?
I think just do without ticking the box now, just for the video, just do it, because I think it will damage your presentation.
Okay, so maybe I don't share the sound because I don't have any sound. Let's see how it goes now.
Yes, no, you still have the strips on the top, but okay.
You see the
yes. Now we see another square on the left.
It was, I mean, when we tested,
or, you know, just present like this.
hold on. Let's try again. You think this is related to?
We start the
Okay.
recording. Okay, go ahead.
Okay, so our group is interested in nanomaterials like nanotubes, nanowires, two-dimensional materials, which have unique properties because of the reduced dimensions, and that can be used as building blocks for making small devices, small sensors or circuits or small machines. And we focus on two main questions. One has to do with the relationship between shape and functionality. We believe that part of the functionality of the nanostructure or the nanomaterial has to do not only with its composition and its morphology, but also the geometric arrangement in the system. So, for example, we were able to grow all kind of interesting structures with nanotubes like serpentines and coils. Another question that interests us is the coupling between different properties, which we also think that increases the functionality of the system. Like, for example, how a mechanical deformation affects the electronic properties of the system, or how optical signal can be translated into an electronic signal. So, for instance, we study electromechanical systems where when a nanotube is twisted, it changes the conductance, and we can use this to make very tiny inertial devices like for gyroscopes. But today I will talk about semiconductor nanowires, which are very important nanomaterials that are used for prototypes in electronics and optoelectronics and renewable energies. Sensors like Hossam, I think he has done many works on biosensors based on nanowires, including the electronic nodes, biointerfaces, and recently there is a lot of interest in using nanowires of topological materials for quantum computing. So these may be the materials of the computers in the future. Now, one of the big problems of using nanowires in technology is that, okay, you can grow very nice nanowires, but normally they grow as a forest. So they grow, for instance, in the vapor liquid solid growth mechanism from nanoparticle seeds, where the material comes from the vapor, dissolves into the nanoparticle, and it grows as a wire. But then you get a very disordered forest, and people then try to harvest the nanowires from this forest and somehow assemble. If you want to have a circuit, this is quite difficult. And what we did a few years ago is, rather than trying to disentangle the tangle, we studied how one can grow ordered arrays of nanowires. And we succeeded in doing this by finding that when you grow nanotubes and nanowires on certain crystalline surfaces, instead of growing up in this disordered way, they can grow in a planar way, crawling on the surface and being guided by surface features. So this is what we call the guided growth. And they can, if the surface is atomically flat, then the nanowires usually they follow certain lattice directions due to an epitaxial effect. So it's related to atomic registry. If the surface is faceted, it can be spontaneously faceted with nanosteps or nanogroups, then they grow along these features that have that are larger than the lattice parameter, and this is called graphoepitaxy. And the combination of epitaxy and graphoepitaxy allows us not only to control the direction of the growth of the nanowires, but also the crystallographic orientation. along which they grow. So there are basically three main mechanisms of guided growth. There's epitaxy, graphopitaxy, which I mentioned, and there's also a artificial epitaxy that we developed recently, where we can grow guided nanowires on completely amorphous substrate by creating the guides using lithographic methods. And they also follow these guides when there is absolutely no atomic registry. We have been using this approach with many different materials like gallium nitride and zinc oxide, sulfide, selenide, telluride, cadmium sulfide, selenide, telluride, bismuth selenide, which all grow by the VLS mechanism. There are also materials that grow by a non-VLS mechanism, like halide perovskite nanowires, which are very interesting for the optoelectronic properties. We can do this on very different types of substrates, like silicon carbide, quartz, spinel, even on scratched glass. You take a glass and you scratch it. This is like a freshman year chemistry experiment where you scratch your beaker and you recrystallize paracetamol, and it crystallizes along the scratches. Of course, also on sapphire, like I showed before. And we can grow more complex structures like a core shell nanowires of two different semiconductors, or core shell nanowalls. And most of the materials that I showed you before, we have integrated into different types of devices, like transistors, logic gates, photodetectors for different ranges from UV through the visible to IR regime, and photovoltaic cells that are based on these core shell nanowires, that we can also, using this guided growth, we can connect many core shell nanowires head to tail in series, and by this way we can multiply the voltage and generate a high voltage in a small surface area, which is very important for miniaturization of power sources for Internet of Things or for a tiny sensor. So we have a patent, and we had a POC project based on this. But in order to be able to do all these things, it is really critical to control the nanowire growth. There are many phenomena that we still don't understand. For instance, gallium nitride tends to grow very, very long, like longer than 1 millimeter, but with a very, very large distribution of lengths. Zinc oxide, on the other hand, can have a very narrow distribution of length, very, very amazingly uniform, but no longer than 10 microns. So we want to understand, how do guided nanowires grow?
5 minutes, Ernesto.
Sorry?
5 minutes.
Oh my gosh. Okay, I will. I think I lost a lot of time with the technical thing. So if you can give me another maybe 2 minutes, I will be able to finish in time. Okay. So so kinetics, to understand the mechanism, like in chemistry, kinetics is a very important tool. In molecular chemistry, normally you use a reaction order to validate or to corroborate or to dismiss different models. In this case, an important parameter is how the growth rate depends on the diameter of the catalyst nanoparticle. Now, in the early days of nanowire growth, which were in the 60s and the 70s, most of the observations were that the nanowire growth rate increased with the size of the catalyst. And this was attributed to the fact that the the material is coming from the vapor phase directly to the catalyst, and then the solubility of the material in the catalyst nanoparticle depended very strongly on the size because of the Gibbs-Thomson effect, which relates the chemical potential to the curvature. And this is the reason why smaller particles have a lower melting point. But later on, during the 20,000s, many cases were observed with the opposite relationship. Namely, the larger than the nanoparticle, the catalyst nanoparticle, the slower the growth. And in some cases, you could even see a non-monotonic dependence where for smaller particles, this was dominated by this Gibbs-Thomson effect. But then for larger diameters, it was dominated by diffusion limitation, where what was observed is that the material cannot arrive directly from the vapor phase into the nanoparticle, but it has to first absorb on the surface, and then the atoms need to crawl or do by surface diffusion. They need to slowly crawl along the surface to the base of the nanowire, and then climb the walls of the nanowire until they reach the catalyst. And this is what is giving this diffusion limited dependence. And this model that combines both the Gibbs-Thomson effect and the diffusion limitation was developed by Vladimir Dubrovsky in Yofa Institute in St. Petersburg. So what we did, and this was the work of a bright student in my group, Amnon Rothman. He started to develop a model that adapted this model of Dubrovsky to the new situation where the nanowire is lying on the surface. So the atoms do not need to climb the wall, but can arrive directly from the surface. We thought that this should affect the kinetics. So here I will not go into the details. We have no time to this, but basically it's considering all the different flows of atoms in and out of the catalyst. He developed some basic equations, but solving the differential equations was, when it became too difficult, we just reached to Vladimir Dubrovsky himself, and he solved all the equations, which were quite complicated, but he was able to come up with a simplified an approximated equation, which had both the Gibbs-Thomson part and the diffusion limitation part. And what was interesting is that we had the diffusion part had a power exponent that represented the dimensionality of the surface diffusion. Namely, if the nanowires, if the diffusion is predominantly along the wire, this dimensionality is 1, like the 1 dimension of the nanowire. But if it is on the surface, then it should be between 1.5 and 2. And we did the experiments. I will not go into the details because we're short of time.
You are over time already, Ernesto.
Sorry?
You are over time, so if you can.
Okay.
Just...
So basically, we find that we have this dependence where the dimensionality of the surface dimension, the dimensionality of the surface diffusion is closer to 2 and not to 1. For many different cases, even with the faceted substrates. So the surface really matters. When we check for vertically growing nanowires, the dimensionality is close to 1 as expected from the model. But then the question is, what really happens when the nanowires grow? To do this, we have to watch how nanowires grow inside the SEM. And this was a magnificent, a very great technological pursuit that we did with a great team, not only of Amnon, but also Ifrat Ashiri Kaplan and Anna Kosoy from the EM unit. So they built a special heating stage to grow nanowires in the SEM. And I will skip this one. I just want to show you that we were able to see nanowires growing along the step. Can you see here a nanowire growing? Okay. And at some point, because there is some non-selective deposition on the surface, the nano groups get a bit contaminated, so the nanowire loses the direction. But we were able to see that the growth is not by jumps, but really at a constant rate. And this is an experiment that was done at FEI that produces the SEM and the heating stages with our collaborators in the Czech Republic, that following precisely our recipe, but with 2 heating stages instead of 1, where they have more control, you can see how the nanowires are growing along the step. And just let me show you. So this nanowire is growing perfectly along the step, but this one is very interesting. And I want just to show this one last movie. What is interesting here is that this nanowire here is growing along this nano group, but the nano groups here, at some point, they are dislocated. So what do you think will happen when the nanowire reaches this region where there is an end to the track, you know, like a train going along the track? So you can see, so far so good. Everything is going straight, perfectly straight. And here it's going to reach soon this region where the tracks are dislocated. So the nanowire gets confused and gets to a different direction. So now you have a much better picture of what is really happening, but we have more experiments going on. So with this, I want to thank my students, especially Amnon and the EM unit students and collaborators, and my wonderful group, and thank you very much for your attention.
Thank you very much, Ernesto. Beautiful presentation. Sorry that we had some technical issues with the Zoom. A million questions. Now we're encroaching into the coffee break. So I don't know if people at least cannot complain with me because I'm shielded by the computer here. But in 4 minutes, we will start the sessions. But what we can do, there's always the chat in here, and maybe we can send questions. And of course, there is, the purpose is just to know each other, at least with this. This is the limitation of this medium. We cannot chat in the coffee room. There's no free lunch, etc. So at least we can start the discussion, exchange email, maybe collaborate. And Ernesto, thank you very much. Hossam, wonderful presentation, both of you. It was absolutely wonderful. So now the program is, if we go back to the program, let me just share it with you 1 second. Oh, sorry. Share screen. So we are